Okay, let's do it. Today, we're going to do section 13.1, types of mixtures. Now, keep in mind, this whole unit is solutions. Solutions are the combination of a solute and a solvent. I'm going to get into all of that. But it's mainly going to be working with things that are in the liquid state for the most part. Now, before I do get into any of that, I want to make sure you guys, this may come up later in the next 2 weeks, but I want to get this out there now. This whole unit is about solutions. A solution is the result of a solute dissolved in a solvent. When I was in school, I got these confused all the time. I have a few ways to perhaps help you straighten them out so you don't get confused too. A solute is the substance that gets dissolved. It is typically less than 50% of the solution. So the Gulf of Mexico is salt water. Salt would be the solute. If you had some cream you put in your coffee and you only put like a few drops of cream in your coffee, the cream is the solute. It is the thing that gets dissolved. The solvent is the majority of the solution. The solvent dissolves the solute. This is greater than 50% of the solution. So salt water, the Gulf of Mexico, water is the solvent. And here's something that may help you remember this. Water is called the universal solvent. So we all know that water dissolves things. It dissolves sugar, it dissolves salt, it dissolves lots of stuff. But if you just remember that water is the universal solvent, that may help you keep things in order from confusing solute and solvent. So I know when I was in school, I just always it's painful. All right, well, that's likely to come up later. I want to make sure I got that out now based on what this whole unit is about. And let's get into types of mixtures. We are sticking to the calendar, by the way, so be sure that if you are not here for whatever reason, that you keep up with the calendar. There should be less math in this unit. There is some, but there's no Charles' law or Boyle's law or combined gas law or ideal gas law. There is going to be some math, but not as much as Unit 12. All right. A mixture is a combination of two or more pure substances. In which each pure substance retains its individual chemical properties. Now, there's two basic types of mixtures. There's heterogeneous and homogeneous. Anybody know what the prefix hetero means? It means different or opposite. If you were in a heterosexual relationship, two different genders, homosexual to the same, hetero means different or opposite. So heterogeneous mixtures do not blend smoothly. That means that each component is going to retain its own characteristics. The individual substances that make up the mixture remain distinct. So they basically don't fully blend. They don't fully blend. There are two types of heterogeneous mixtures. They're called suspensions and colloids. Let's talk about suspensions first. This is a vocab term. You guys have a vocab quiz this week. That's going to be your last grade for the third quarter. It's a mixture containing particles that settle out if left undisturbed. An example is muddy water. So let's say that Colby gets a glass of water here, and he's going to put some mud in there, and then he stirs it up with a spoon. So let me add some mud. There's going to be some mud on the bottom. So he stirs it. Well, the whole container is going to look brown and nasty, muddy water. But Colby stops stirring. In just a few minutes, all that mud is going to settle back on the bottom. This is known as a suspension. Oil and water are polar and nonpolar, so they don't mix. Oil is hydrophobic. It cannot mix with water. If you put it in a blender, they're not going to mix. They just don't react with each other. Say that again? Like emulsifiers? No, we're not going to have to know about those. Okay. Also, if you want to prove that it's a suspension, pouring a liquid suspension, like muddy water, through a filter will also separate out the suspended particles. Now, I don't know if you guys have been downstairs yet where the turtle pond is, but it looks a lot different now, doesn't it? I spent 2 days during spring break trying to clean it all out. And the pump has been broken since August, which is why the water turned so green and gross. Did that water, that green water, you all have walked by that pond, hopefully you've at least looked at the pond and you saw it the way it was before. That green stuff was algae. It was with the water. So could I have taken a net and just scooped out the green stuff from the water? No. That means that that was a pure mixture. That was homogeneous. And so when I was over here on Tuesday and Thursday of last week, I could not have just taken a net and scooped up all the green junk and then the water would have been clear. The water and the green were one. It was homogeneous, which we'll get to momentarily. But what if there were things like leaves and pollen and maybe a pencil eraser floating in the water? Could I have taken a net and scooped that out? Yeah, that would be heterogeneous. Those things were distinct from the water. So I took this big pump and I pumped out all the green water because I could not just take a net and skim along the surface and get all the green stuff out. The water and the green algae were one and the same, so it all had to go. It all had to go out. But as leaves and pollen are falling in there, I can easily scoop those out. The leaves and the pollen, those were going to be components that would not blend in. And so the water and the pollen and the leaves were distinct from each other. That would make that heterogeneous. Which, by the way, speaking of that pond, it's clean now. The waterfall's going. It looks great. If you guys happen to see some jerk, quite honestly, it's mostly freshmen, messing with the pond, throwing stuff in there, harassing the turtles, say something, because the turtles can't fight for themselves. They need you to do that. Or text me. Say, Mr. Thorson, saw some kids screwing around with the turtle. I said something to them. You might want to check it out. Let me know. But speak up for the turtles. They can't defend themselves. I don't want some kid being a butthead and hurting them, which has happened. Okay? All right. Now, so there are two types of heterogeneous mixtures. The other one is going to be a colloid. A colloid is a heterogeneous mixture of intermediate sized particles. So these muddy water is just a suspension. The mud is big. Heterogeneous would be, a colloid would be something that's maybe along the size of macromolecules. So they're microscopic, but they're still kind of large on the microscopic scale. Colloid particles are smaller than suspension particles. They can be between 1 nanometer to 100 nanometers. They do not settle out. But you can separate them. But because they're so small, they don't settle out. You need like a machine to separate the solute from the solvent. The solute are the particles. The solvent is the liquid. Milk is an example of a colloid. Let's see if you guys know this. What is skim milk basically? Water. It's basically white water. Yeah, there's nothing in there. What is whole milk? Cream. Not cream. I kind of know where you're going with that. But you go to Publix and they have like the purple capped jugs of milk. They have the blue capped. They have the red capped. They have the sky blue capped. They all mean something. I think red is whole milk. Purple is 2%. Light blue is 1%. Green is skim. I think that's how it goes. I might have my colors mixed up. Whole milk is all the fat. It's all fat. There's a lot of fat in there. Skim milk is none. So what's 1%? And what's 2%? Well, what it means 2% and 1% what? Fat. So 2% milk is 2% fat, 98% basically white water. 1% milk is 1% fat, 99% white water, and then skim milk is just nothing. Well, how do they get the fat out of there? You can't just take a net and scoop it up like you could muddy water or pollen or leaves. You have to have a machine. You have to have machines that are actually capable of getting those very, 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 very small fat particles out. Yeah. So you drink skim milk, you might as well be drinking water. Pretty much. It's more, some people just drink it for flavor because, would you want to have water with your cereal? No. Milk still has that flavor, but there's no fat in skim milk. It's basically white water as far as nutrition is concerned. There is some protein in there, but there's no fat. All right. So what is the solvent? Is it the majority or the minority of the mixture? Okay. So the most abundant substance is the dispersion medium. What the heck does that mean? Dispersion means spread out, and the medium is like the cause or the area. So when you have literally the Gulf of Mexico, the water is the dispersion medium for the salt. The water is the reason the salt is able to spread out. When you have a glass of milk, the actual liquid is the reason that the fat can distribute throughout the milk. Now, when you have a glass of milk, the fat is not going to just settle down on the bottom if you leave it on your counter for half an hour. Those particles are so small that they don't settle out, that they continually mix throughout the substance. But it is Heterogeneous. And the reason why milk is heterogeneous is because you can separate the fat, which is the solute, from the liquid, which is the solvent. You just need a machine to do that. But the fact that it can be done means that it is it's heterogeneous. Okay. Now, when it comes to heterogeneous mixtures, let's talk about the Brownian motion and Tyndall effect. These are definitely be on your test. All right, Brownian motion. Dispersed particles in liquid colloids like milk make jerky, random movements. Oh, Carson, while I was thinking of this, because you asked, I'll just address this to you. You know, people in college do some pretty silly stuff. I will say when you go to college, be smart with your time management. You do have classes, homework, tests, yeah. But obviously some people have some fun. And I remember some guys I was friends with, they did this milk challenge where they had to drink a gallon of whole milk in 1 hour. Now, what do you think your body can process better? Whole milk or skim milk? Skim milk. It's white water. There's less fat. There's no fat, actually. So the rule was you had to do whole milk. Well, one of the guys cheated, and he had, whole milk. I think at Publix they'll have the red cap. He put a red cap on his skim milk jug, and he won. And he was fine, because if you drink whole milk too fast, you'll throw up. Your body can't process that much fat and lactose at once, so you'll just feel like really nauseous, and it'll come out of you like a geyser. But he did skim milk in 1 hour, and he's like, doesn't bother me at all. And so we look closer at his jug, and he cheated. He had skim milk, which is much easier to digest than it is for whole milk. Whole milk is just, for lack of a better word, chunkier. And so if you ever hear about those whole milk challenges and people puking, or not whole milk, but just the milk challenge, they were doing whole milk just because there's a lot more solute in there. All right. Now, the particles within milk, the reason why they don't settle on the bottom is because of the Brownian motion. The erratic movements result in collisions. For those of you that have already started your vocab, is this one on your list? Do you know? It might be. I'm pretty sure it's on your test. I know that for sure. I don't know if it's on your vocab quiz. Brownian motion. It's named after the scientist that discovered it, Brown. Results from collisions of particles so like with milk, you have particles of the actual liquid colliding with particles of fat. With things like a suspension, the particles are far too big. And they're going to be just moving in random areas. So if I have a region here, let's say every one of these little black dots is a particle of fat in milk. They're just going to continually collide, and they're going to go in random movement. It's kind of like elastic collisions where they're just going to collide with each other, or they're going to collide with particles of the medium, or they're going to collide with the walls of the container. They're just going to continually just bounce and bounce and bounce and bounce and bounce off each other. But what they will not do is they will not settle on the bottom like mud would. These collisions prevent the particles from settling out. Yes, Arsha.
What happens if they like cool or if they freeze the colloid?
It'll still be suspended. It's just going to be, the whole thing will be frozen through.
So they won't like sink even if they lose energy?
No. All right, and then the next one, I wish I could give you guys a visual because it's actually pretty cool to see. The next one is called the Tyndall Effect. I'll try to describe it as best I can for you. This happens a lot when you're driving. Something you all, is anyone here in driver's ed? Did they tell you not to use your brights in the fog? Okay, that's because of the Tyndall effect. So in this, concentrated colloids are often cloudy. Dilute colloids sometimes appear, and I want to underline that word, looks can be deceiving. They appear as clear solutions. But there's more to that than meets the eye. The dilute colloids appear to be homogeneous solutions. Because their particles are so small, you don't see them. I mean, do you actually see the water droplets that make up fog? You know, I live over on Harbor Island, and when I'm driving to plant in the morning when it's really foggy, if you're driving by Jackson's Bistro, you're going over that bridge by the convention center, you cannot even see the skyline. Like, the buildings are gone. It's like Skull Island. I'm going to see King Kong. There's nothing there. But as you get closer, oh boy, there's the buildings. Little tiny microscopic water particles are making up all that fog. You can't see it, but they're still there. Now, here's where it gets kind of fun. The dispersed colloids can reflect light and scatter light. Maybe I'll try to pull up a YouTube video that might show this with vinegar and water. So the reason why they tell you not to drive with your brights on in the fog, the light is not, the headlights is not a flamethrower. You're not going to clear a path in the fog just by having bright light. It doesn't work that way. So let's say that you're driving, and this is important, be important for you because most of you are 16, you're starting to drive. Let's say that you're driving, there's no fog, okay? Your headlights are going to shine forward like this. They're going to shine straight ahead. That's normal. But then we have foggy conditions. So let's just fog all over the place. This is all fog, all right? If you shine your brights, the light is going to reflect off of here, and here, and here, and just reflect everywhere, and can reflect right back at you. Because every little particle is acting like a mirror. And if you get it at the right angle, those brights that you're shining can come right back at you, and you can't see anything. So when they say have your low beams on, well, do I have to setting for my low beams? No, you just turn on your headlights and don't turn on your brights. Your high beams are your brights when it's really, really dark out in the middle of the woods. but your low beams are just your regular headlights. Don't do that. Well, and another example would be, and this is what I have on your PowerPoint, is let's say you have an aquarium, and there's water here in the aquarium. You have a flashlight, and there's no vinegar, for instance. There's no vinegar that's in the aquarium. The light is going to shine right through. But let's say that you have an aquarium and there's vinegar in the water. You have your flashlight. You can do this at home. You shine your flashlight, it's going to illuminate the whole thing. That's the Tyndall effect. The beam of light is reflecting off every little particle of vinegar, and every little particle of vinegar is acting like a mirror, and it's going to illuminate the whole aquarium. The reason why this happens is because there is no solute in the solvent. Here, there is solute in the solvent, and it's reflecting the light. That's the Tyndall. Yeah.
If there's less solute, will it like reflect less?
Yeah, it'll reflect less. You know, dense fog is not going to be as reflective as minimal fog, but it still can reflect. Okay. So maybe I can try to find a video. I don't know if I can. I haven't looked it up yet. Let's pause this recording.